All right. Welcome everyone to the 60th meeting of New Directions in Group Theory and Triangulated Categories. Today our speaker is Rhiannon Savage from the University of Oxford, and she'll be speaking to us about algebra and geometry in monoidal quasi-abelian categories.
Hi everyone. Thank you so much for inviting me, Rhiannon. Great. So I'm just in the second year of my PhD, so this talk's going to be quite general and it'll be mainly like ideas focused. So I'm going to be talking about the following things. So I'll give some motivation as to why we're interested in studying quasi-abelian categories, and I'll tell you what exactly I mean by a quasi-abelian category. I'll then show why quasi-abelian categories have interesting properties for doing homological algebra, and I'll show that by talking about some Koszul duality results. And then I'll talk about how we can build up a model of derived analytic geometry using quasi-abelian categories. Okay. So one point of view on algebraic geometry, use it as algebra plus topology. So we might think about schemes as glued together from affine schemes using the Zariski topology. And this is the idea taken by Towin and Vaquier in their paper under spec Z. They consider algebraic geometry relative to a symmetric monoidal category C. Normal algebraic geometry then occurs when we take C to be the category of algebraic groups, abelian groups. Great, so we can extend that idea to homotopical algebraic geometry if we replace C with some symmetric monoidal model category or infinity one category. And derived algebraic geometry then is when we take C to be the category of simplicial modules over some simplicial commutative ring K. Obviously, there are lots of other approaches to derived algebraic geometry, but this is the one that I'm familiar with and we're going to be using today. So that's derived algebraic geometry, but what about if we were going to think about derived analytic geometry? So we could choose some suitable monoidal category C, and then replace our simplicial commutative ring K with some simplicial commutative monoid in that category. By monoid, I just mean like an algebra in a monoidal category, not the other notion of monoid. What category should we choose? The categories of interest for us will not be abelian categories, but will instead be quasi-abelian. So we'll be talking about the category of Banach spaces, categories of bornological spaces, etc. So a good theory of quasi-abelian categories will help us when we're thinking about these ideas in derived analytic geometry. So I should say that this is not my idea, but it's builds upon work by Federico Bambosi, Oren Ben-Basat, Jack Kelly, my supervisor Kobi Kremnizer, and Devarshi Mukherjee. So I'll be talking more about that at the end. So let's think about these quasi-abelian categories. We ideally want a nice category in which we can do homological algebra. So when we're thinking about homological algebra, we usually start off with short exact sequences of modules over a ring. And then we can extend these ideas to abelian categories by considering the Freyd-Mitchell embedding theorem. So every small abelian category emits a fully faithful, I should say I've got a bit of a cold, so apologies if I lose my voice. So every small abelian category emits a fully faithful exact functor into the category of modules for some ring R. So that's how we extend homological algebra to abelian categories. We can go even further and think about exact categories. So Quillen's exact categories were introduced to generalize these results you've got an additive category with a collection of short exact sequences satisfying some nice properties in which to do homological algebra. And in fact, every exact category emits a fully faithful exact functor to some abelian category A. So you might be like, why can't we just work with a general exact category? The categories of interest to us are exact categories, but the full formality of exact categories is a bit too much for us. So we want something in between a full exact category and an abelian category. So as I said before, we're thinking about derived analytic geometry. And one category of interest to us there is the category of Banach spaces. So consider the category of Banach spaces. This category is not abelian, and it's one of those key examples of categories which is not abelian, because there are morphisms that don't satisfy the first isomorphism theorem for Banach spaces. This category does have an exact structure though, so we can define the notion of a short exact sequence in this category. So a short exact sequence would be a sequence where the image of F is isomorphic to the kernel of G as usual, but then we put a condition that says that F satisfies the first isomorphism theorem for Banach spaces. So that's so that we get these well-defined short exact sequences. So the collection of all such sequences does define an exact structure on the category of Banach spaces. So we're going to take this model for when we define our quasi-abelian categories. And we want quasi-abelian categories to have this maximal short exact structure. So okay, so let's think about what condition we put on F there. So suppose that we have some additive category E with all kernels and cokernels, and suppose that F is a morphism in E. So we can consider the decomposition as follows. So we've got the kernel and the cokernel labeled here, and then we can define the image, the co-image of F to be the cokernel of the kernel, so this map here, and we can define the image of F to be the kernel of the cokernel, so the kernel of this map here. And using our universal properties of kernels and cokernels, we have an induced map from the co-image to the image. And so we will say that F is strict if this map is an isomorphism. So if in many of our familiar categories, this just corresponds to F satisfying the first isomorphism theorem. So in any abelian category, every morphism is strict. But to define our quasi-abelian category, we just want some of the morphisms to be strict. So this led to the introduction of these quasi-abelian categories by Schneiders in 1998. And he said that an E, which is additive with all kernels and cokernels, is quasi-abelian if it satisfies the following properties. So if we have a pullback square, we want that if this morphism F is a strict epimorphism, then F dash is a strict epimorphism. So this says that cokernels are stable under pullback. And a dual condition saying that if we have a push-out square, then if F is a strict monomorphism, then F dash is a strict monomorphism, i.e. kernels are stable under push-out. So we have these two conditions, and this will allow us to define an exact structure on E. So in fact, we can define the notion, not just yet. So examples, as we've already talked about, include the category of Banach spaces, as well as the category of Frechet spaces, so locally convex metrizable topological vector spaces, and more generally, just the category of locally convex topological vector spaces. Schneider's was initially motivated by studying the categories like sheaves with values in the category of filtered abelian groups. But we'll be more interested in these kind of categories which are useful in function analysis. So as I was saying earlier, we can define an exact structure on a quasi-abelian category. And this comes from the following definition of a strictly exact sequence. So a sequence like this is strictly exact if the image of F is isomorphic to the kernel of G, and we also want that F is strict. Okay, and the collection of all such short exact sequences like this will define our exact structure. Okay, so we've got quite a few examples of quasi-abelian categories already, but we also have a way of constructing new quasi-abelian categories from old ones, and that comes from considering the notion of an ind object. So this is a way of adding filtered co-limits to your category. So if you start off with a category C, the category of ind objects in C would be functors from a small filtered category I into C. And then what are the morphisms? Well, if you've got two functors X and Y, two ind objects X and Y, then you would be able to think about maps from Xi into Yj, and then the total collection of morphisms will be given by taking first the co-limit over J, which is the second variable here, and then taking the limit over I. Okay.
Can I ask a quick question?
Yeah, go for it.
Can you go back to the previous slide? So,
yeah.
So is F strict if and only if G is?
Yeah, so it's a dual condition. So you can take F to be strict or G to be strict. Yeah.
Okay. Thanks.
Yeah. That's a good question. Yeah. So we have this category of ind objects, and in fact we can just define take those where we have all the system morphisms being monomorphisms. That will prove to be very useful later. So we call this an essentially monomorphic object. Oh gosh, my cough is so bad. Which is one isomorphic to a system where for every I to J in I, the corresponding map Xi to Xj is a monomorphism of C. So we'll denote the category, denote this category by in subscript, superscript C. And in fact, you can prove just by checking at each level that if E is quasi-abelian, then the category of ind objects and its subcategory of essentially monomorphic objects are also quasi-abelian. So we've found a new way of constructing quasi-abelian categories, which will turn out to have slightly nicer properties. So indeed, if C is concrete, and the functor from C to set preserves and reflects monomorphisms, then a subcategory of essentially monomorphic objects is also concrete. So in general, the category of ind objects is not concrete. And also, for example, if we take C to be the category of Banach spaces, then these two categories are quasi-abelian. And we've also created a category such that in Banach spaces and in M-Banach spaces are bicomplete categories, so complete and co-complete. But the category of Banach spaces is only finitely bicomplete. So for some purposes, taking this category or this category can be more useful. Okay. So I'm actually going to call this category of essentially monomorphic ind objects in Banach spaces something a bit more catchy. So I'm going to call this the category of complete bornological spaces. If you've seen bornologies before, great, but if you've not, then you can kind of think of bornologies as if you, well, in topology you care about open sets, but in bornology you care more about bounded sets. So I've called it the category of complete bornological spaces just by abusing a bit of notation, but it's just, if you define it in the alternative way, it's isomorphic to the category of essentially monomorphic ind objects in the category of Banach spaces. I think I just got a question. Is your K a Banach field or a general Banach ring? So here I've just taken it to be a valued field, but you could just take it to be like a Banach ring and then consider Banach modules over that as well. But we're just going to work with fields for this talk. Okay. And in fact, there is actually a fully faithful functor from the category of Frechet spaces to the category of complete bornological spaces. Okay, so we've got lots of new examples of quasi-abelian categories. And now we'll talk about how we can use quasi-abelian categories. So my example will be from Koszul duality. And so this is a key notion in representation theory and originates by thinking about certain modules over, started with this case and then was extended to various kinds of derived equivalences between modules over algebras and modules over duals. So in 1978, Bernstein, Gelfand, and Gelfand showed that if we have a finite dimensional vector space U over field K, then we can obtain a projective resolution of K as follows. So S of V here denotes the symmetric algebra over V, and this kind of big wedge symbol denotes the exterior algebra, with the 2 saying that this is the second graded part of the exterior algebra. So we've got these are all projective SV modules, and they are generated in, so for the module in degree I, it's generated by its ith component, as you can see. And in fact, you get a derived equivalence between graded SV modules and graded modules over the exterior algebra of V star. So this was then generalized by Beilinson, Ginsburg, and Sergel in 1996 to objects called Koszul rings. So SV and exterior algebra V are both examples of Koszul rings, and we get a slightly more general derived equivalence of categories. Okay, just going to have a little glass of water. So I have showed that this kind of construction can be generalized to quasi-abelian categories. What do I mean by that? We're going to show that if you take some monoids in a certain quasi-abelian category, you can get a well-defined notion of a Koszul monoid, and also show that in this case you obtain an equivalence of some subcategories of the derived categories of graded modules. So we need to develop within our quasi-abelian category what it means for something to be projective. We don't yet know what the derived category is in this context either. So indeed, like defining projective objects is quite easy. You can just say that an object is projective if if maps from P into something as a functor is strictly exact. So by strictly exact, it means quite intuitively that it sends strictly exact sequences to strictly exact sequences. Okay, so suppose we take some bicomplete closed symmetric monoidal quasi-abelian category. So for example, the category of Banach spaces. Oh wait, no, sorry, the category of inter-Banach spaces. Remember that the category of Banach spaces is not bicomplete. And suppose that A is some positively graded algebra object in E. Then we can loosely define what a Koszul monoid would be in that situation. So the definition of pre-Koszul is not that important. It just means that each AI is projective as a module over A naught, and A naught is injective over itself, and satisfies some nice conditions on the Hom sets. But we want A naught to have, as with K in the previous case, to have a nice projective resolution where we're thinking about strict resolutions because we're working in the quasi-abelian category case. So we'll have some projective strict resolution of A modules, and we want each PI to be generated by its degree I component over A naught. So you see that this is exactly the same as in the case of the symmetric algebra case. So keep that as like a little example in your head. Okay, so this is what means to be Koszul. But we want to get some nice derived equivalence. So what does a derived category mean in a quasi-abelian category? So we would usually take the homotopy category and localize at quasi-isomorphisms when we're dealing with an abelian category. But we don't know what a quasi-isomorphism is because we don't know what, like homology is not well defined in this quasi-abelian category because not all morphisms are strict. But we can instead use a characterization of quasi-isomorphisms, which says that a morphism of chain complexes is a quasi-isomorphism if and only if its cone is exact. So we can define that in a quasi-abelian category. And instead, we want our cone of our morphism to be strictly exact. So we can form the derived category by localizing the homotopy category at the class of all strict quasi-isomorphisms. So it's not too dissimilar to the usual definition. Okay. And in fact, we actually have an equivalence of derived categories between the derived category of in Banach spaces and the derived category of modules over the derived category of the category of complete bornological spaces. So when we're doing derived stuff, we can work with either of these categories, depending on which one we prefer. Okay. So suppose that E is bicomplete closed symmetric monoidal with enough flat projectives. Then with some conditions on A. We introduce some kind of left dualizable condition, which essentially means that each graded component of A has a nice dual. In this case, there is a quadratic dual. I've introduced quite a lot of words which I haven't talked about before. But importantly, this dual is Koszul and satisfies the following condition. It says that if you take the right quadratic dual of the left quadratic dual, then we get A back. So with our symmetric algebra case, we had that the exterior algebra over the dual vector space was its quadratic dual, which was also Koszul. And in this situation, we get the following result. We get that there's an equivalence of categories between, so these are certain subcategories of the derived category. We have to kind of consider the internal grading of the category of graded A modules. So you get this kind of complicated derived category. But it says that some parts of the derived category of graded A modules correspond to some parts of the derived category of graded A Schweik modules. Okay, so this is exactly the same result as proved by Bayes-Ginsburg's circle for Koszul rings over semi-simple rings. But this is more general in that A is just some nice monoid in a quasi-abelian category. Okay. So the actual statement of this is not that interesting, but the proof of it I find very interesting. We essentially are proving statements of the following form. So we want to show that a functor between chain complexes on E, where E is some quasi-abelian category, to chain complexes on F, where F is another quasi-abelian category, induces a functor on the level of derived categories. So we'll use something called the left heart construction in order to do that. And this essentially, this is one of the most important results about quasi-abelian categories. And it says that if you take a quasi-abelian category, then we can embed it into an abelian category, which is called the left heart of E. There's a characterization of this left heart as the heart of a T structure defined in the homotopy category. But I'll talk about another way of thinking about it in a bit. And this actually induces an equivalence on the level of derived categories. So it says that when you think about quasi-abelian categories and the derived categories, we're essentially just thinking about what happens in the abelian case. So this left heart construction can be described as following. So we can consider complexes in the homotopy category where we have two objects with x0 in the 0th position and F being a monomorphism. And we can localize at the multiplicative system formed by morphisms such that we have a bicartesian square like this. So bicartesian meaning pull back and push out. So we get an abelian category in this way. And therefore we can use that to prove this statement. In our Koszul duality case, we've got E being graded A modules and F being graded A Schweik modules. So we need to show that F preserves strict quasi-isomorphisms, but remember that being a strict quasi-isomorphism just means that the cone is strictly exact. So we can just show that F preserves strict exactness. So consider some strictly exact complex and consider its image under F. We can then take our embedding of F, which is a quasi-abelian category, into its left heart. And then we just need to show that this complex IF of C is strictly exact. And we can use that, we can do that using the following result, which is just a corollary of the previous one and says that a sequence is strictly exact in E if and only if under the embedding we get an exact in the usual abelian category sense sequence in the left heart. So indeed, in the proof of the Koszul duality result, we just used the usual theory of spectral sequences in abelian categories to prove the necessary things were exact. So this embedding of an abelian category into, quasi-abelian category into an abelian category means that you can simplify lots of proofs by just using what you know already for abelian categories. So let's think about something a little bit different. And this is thinking about derived analytic geometry. So as I said before, we can kind of think of relative algebraic geometry as, so we can think of geometry as some algebra plus topology. So we'd have schemes which would be glued together from affine schemes. But we notice that the category of affine schemes is isomorphic to the opposite category of commutative rings, or equivalently commutative monoids in the category of abelian groups. So what we do in relative algebraic geometry is replace this category of abelian groups with some other symmetric monoidal category C. And then similarly, we just define an affine scheme to be just an object in the opposite category of commutative monoids over C. And then if we can find good notion of the Zariski topology on the category of affine schemes, then we can construct an idea of what a scheme relative to C means. Okay, so kind of has analogies with what we were talking about before. We just replace our like abelian category of rings, with like category of monoids in a monoidal category. And if you take anything away from today, that's the kind of main message. So as I said before, if we chose C to be some nice quasi-abelian category, we could get a nice version of like analytic geometry out of this. So I'll talk about how we could maybe do that in the rigid analytics geometry situation. So I'm not going to talk too much about this because it's definitely not my area of expertise. And also, so in rigid analytic geometry, our main objects are affinoid algebras, which we glue together using the G topology to get rigid analytic spaces. Don't worry too much about what this all means. So an affinoid algebra for us will just be a kind of a Banach algebra over some non-Archimedean valued field K. So you could take the set of p-adic numbers as your non-Archimedean valued field. So this would obviously suggest that we could take the category of Banach spaces. So Oren and Kobi developed this theory of rigid analytic geometry by defining a categorical analog of the so-called G topology on affinoid algebras. So I'll just explain what this categorical analog of the G topology is, and show it will kind of exhibit the strength of this relative approach because it's all very general and easily applicable to other categories. So we can work with any finitely bicomplete close symmetric monoidal quasi-abelian category with enough projectives. So the category of Banach spaces is an example of such a category. And we can consider a morphism of affines in that category. The induced morphism of modules is derivable to functor on the derived category. So this is the derived category of a quasi-abelian category. And we'll say that F will be a homotopy monomorphism if the induced morphism here is fully faithful. And the corresponding morphism would be called a homotopy epimorphism. So when we're defining these topologies, we're looking for a collection of covers satisfying some nice property, and we want there to be a good notion of like surjectivity. So this is like the motivation for why we're defining this homotopy epimorphism condition. And this will actually correspond to the usual covers in the G topology. So maybe a more familiar definition is as follows. So if F is a morphism in the category of commutative monos of E, then it would be a homotopy epimorphism if and only if the derived tensor product of B with itself of A is isomorphic to B in the derived category. So if we kind of cross out the word epimorphism and take away the L, this is a familiar characterization of what an epimorphism is in the category of modules. So just
I have a question.
Oh, yeah, hi.
Hi. In your previous slide, you took the bounded derived category, but in this one, you have the unbounded one. Is there any reason for this difference? So when you define homotopy monomorphisms?
Yeah, I think this I think this is it's a fine take the bounded derived category here.
Okay,
I think
the
this
equivalent criterion removes the bounded derived category for some reason.
Yeah.
Okay.
Well, I think because this will be in, maybe this is naturally in the bounded derived category anyway.
Okay.
Okay. So this is our definition of a homotopy epimorphism. And we need to define a good notion of surjectivity. So this definition of the topology we defined at the moment was adapted from one of Cohen and Verzossi, but it was simplified in the following way, which is maybe not that intuitive, but when you see it kind of proved, it just naturally falls out. So if we have some subcategory of affines, closed and defined products, and satisfy nice conditions such that the base change of a homotopy monomorphism is a homotopy monomorphism, then we just want to consider modules as follows. So we just want to consider this category that they call RR quasi-coherent in modules, which is just A modules such that if you have some homotopy epimorphism A to B, we have an isomorphism of the derived tensor product with just the underived tensor product. Okay. So I think they're doing more research in this with these objects as well. So this now allows us to define a topology on A. So remember that A was closed and defined products and had this base change property. And they call this the formal homotopy Zariski topology. So in the usual Zariski topology, we have covers being surjections, but here we have homotopy epimorphisms instead, and we want our morphisms to satisfy, morphisms of modules satisfy this like to be the tensor product to be conservative, in the way that a morphism of modules would be a morphism if and only if the corresponding morphisms on the covers, tensoring over the covers, are isomorphisms. So this is very general topology, and in fact, if you just take E to be the category of Banach spaces and A to be the opposite category of alpha-monoid algebras, this topology lines up with the weak G topology. So this seems to be a good topology to define, and we've shown that this relative to analytic geometry lines up with the classical case. So it gives us a new way of thinking about rigid analytic geometry. We can also define other versions of relative geometry. So for other cases, we might want our category to be bicomplete. So as we mentioned earlier, we can instead take the category of in-Banach spaces or complete bornological spaces for some valued field K. And then we get lots of other nice geometries as well. So yeah, you can consider dagger algebraic geometry. So I think Federico is here as well, as relative to the category of complete bornological spaces. Other geometries coming such as complex analytic geometry, relative to the category of complete bornological spaces over C, and also a version of analytic geometry over F1, so the field with one element. So this is the current state of derived analytic geometry, and there are various other papers coming out, I think, soon. So we can, in particular, one talking about the foundations of derived analytic geometry, similarly to derived algebraic geometry. So as I mentioned earlier, you can view homological algebraic geometry, which is just derived geometry relative to some non-isometric monoidal model category, with derived algebraic geometry being geometry relative to the category of simplicial modules over a simplicial commutative ring. Okay. And then the idea with derived analytic geometry is done relative to the category of simplicial modules over K, where K would be some simplicial monoid in the category of complete bornological spaces. So a good theory of quasi-abelian categories is very useful here because our category of choice is quasi-abelian. So my research is focused on proving a representability theorem for derived stacks in this context. And we also hope to show some Koszul duality results in the sense of Lurie for this context. Okay, so thank you for listening.
Thank you, Rhiannon. Can we all unmute ourselves and give the speaker a round of applause, please? Okay, if you have any questions, you can ask them now.
So in the definition of Koszulity for a monoid, you mentioned it should be pre-Koszul. Does this include something like A0 being semi-simple?
So the idea is it's more general than being semi-simple. So in their paper, they choose semi-simple as like their criterion, and it simplifies lots of constructions, but it's not actually necessary. Mm-hmm. So any semi-simple ring will be.
Okay, great.
But not necessarily the other way around.
Okay, thanks.
Yeah, thank you. Any other questions? There were a couple of comments in the chat, Rhiannon. I think one of them was addressed by you, and there were two more,
Okay.
but they're not questions.
I think maybe they've been answered already.
Yeah, they're not questions. They're just
Yeah.
things that exist in the chat.
Yeah.
Any other questions? I had a general question about these derived categories that you are constructing from your quasi-abelian categories. So is there any way of like detecting or tracing generation properties of these derived categories? Like, are they always compactly, I mean, when are they compactly generated, or when are they well generated, or things like that?
Oh, I don't really know, to be honest. I've not really seen like compactly generated for derived categories before. So the best place to look for anything like this is in the Schneider's book called Quasi-abelian categories and sheaves.
Okay. Thank you. Any other questions? Anyone? All right, yeah, thank you. Yeah, thank you very much. Okay, in that case, let's thank the speaker again. So there's another comment or something for me.
Yeah, I was just saying
you.
that you can check
Yeah,
these
thank you,
generation properties in this paper. And in particular, short answer to your question is that, yeah, exactly. I think even Federico writes this. These are exactly L1 Banach spaces that gives you a set of compact generators for the derived category of int Banach spaces.
Yeah, thank you very much. That's very neat. There's also a question of choosing universes.
Yeah.
Okay. Thank you, everyone. Let me stop recording now.